Welcome to Amplified Education, your exam prep friend. Today we are looking at electrodynamics, particularly motors, and the motor effect. Please pause the video and try the questions on your own. The question reads, the dot below represents a wire with current coming out of the page. Draw the magnetic field around the current carrying wire, clearly showing the direction of the magnetic field. So here, in order for us to determine the direction of the magnetic field around the wire, we could use the right-hand grab rule. And in the right-hand grab rule, your thumb represents the direction of the current, and your curling fingers represent the direction of the magnetic field. So the magnetic field goes around the wire as shown, or as I'm drawing it here. And your fingers, if you use the right-hand grab rule, should be curling anti-clockwise. Okay. The conductor is now placed in a permanent magnetic field as shown below and experiences a force towards the left. So the force is towards the left and the current is coming out of the page. So what we need to do here is that we need to use, obviously, Fleming's left-hand rule to first determine the direction of the magnetic field. Because the question says we must draw the resulting superimposed field, superimposed magnetic field that is observed when the magnetic field on the current carrying wire interacts with the permanent magnetic field. So using Fleming's left-hand rule, our thumb should be pointing left. Remember, Fleming's left-hand rule, our thumb, our middle finger, and our pointing finger should all be at right angle to each other. The thumb is pointing left, right? Your middle finger is pointing out of the screen, representing the current, and the thumb represents the force. And our pointing finger represents the direction of the magnetic field from north to south. All right. And so this would be the direction of the B field. And if we just draw maybe here, the magnetic field around the wire. So that circle that I'm drawing now represents the magnetic field around the wire. And then what I'm going to do is that I'm going to represent the permanent magnetic field of the magnet using a black pen. And that would look like that. And those magnetic field lines would actually point that direction. They would point that direction. Okay. Right. And we can see here, remember, we had already said that the magnetic field around the current carrying conductor is anti-clockwise. So it points in that direction, all right? And it's now parallel to the magnetic field of the permanent magnet. And so here, there's definitely a build-up here of magnetic field there because all those magnetic field lines are pointing in the same direction, right? And so this would be how the superimposed field would look, simply because remember, if you have a north pole at the top and let's say a south pole at the bottom, the magnetic field for the permanent magnet will just be parallel lines. It would be what we call a uniform field, all right, that would be the case. But this is a superimposed field that is a result of you placing a current carrying conductor in a permanent magnetic field. And then the next question says, is pole X the north pole or the south pole? So according to what we've drawn here and the magnetic field lines moving from Y to X, Y is definitely north and X is south. Right, so X is the south pole. Okay. Now we've done that part. The next question now says, the wire is then placed parallel to the field, all right, or to the magnetic field shown below. Remember, we already know that X is south, right? And Y is north. And then now the current is moving parallel to the B field. So these two now are parallel to each other. Okay. They are parallel to each other. The current is parallel to the B field. So that's how now the wire is placed. Whereas in this particular case, the first case drawn here, that was not the situation, right? So what questions are coming up from this? Let's see. The question should be here. Yeah, the question 1.4 there at the bottom says, explain whether the wire will experience a force using a relevant formula. Now, the force that is experienced or exerted on the wire is given by the mathematical expression length times the strength of the magnetic field, which is the B field, multiply that by the current strength in the wire, sine theta. All right. And if you place the wire such that it is parallel to the B field, the angle theta there between the B field and the current should be zero. It's actually zero, right? Because in the first case, remember, in the first case here, the current is perpendicular to the B field, right? So the current there in that particular case, remember, if your eye is here and the current is coming out of the page, the field was cutting in that way. So that's the difference. The field was cutting that way, and the current there and the field were at right angle to each other. So here theta was equal to 90 degrees, right? That's the difference. Here, the B field is parallel to the current, which makes theta equal to 0 degrees. And the sine of 0 degrees would be equal to 0, which means the force would also be equal to 0. And so here, based on what the question is asking, the question is saying, explain whether the wire will experience a force or not using the relevant formula. We can see that mathematically, if the current and the magnetic field are parallel to each other, the wire will definitely not experience a force. And that is what we are seeing there. All right. So that's the first part of those questions. Let's go down and have a look at some more questions, okay? So the next set of questions that we can see that it says the force experienced by the wire can be calculated using the formula that we've just seen now, F equals LBI sine theta. A group of students set up an experiment to investigate the relationship between the strength of the magnetic field and the force experienced by the wire. We can see the results given there. The first question says identify the independent variable. And so we can see that it is the magnetic field strength that has been changed, either by obviously changing the magnets. And so if that is the case, then the independent variable would be the magnetic field strength, B, which is measured in Teslas. Okay, so that's magnetic field strength, or what I would like to refer to as the B field. Now, the dependent variable we can see is represented on the right-hand side on that table. That is what they are measuring, right? As they change the magnetic field, the force exerted on the wire is definitely changing, and you can see from the table that it is increasing. So the dependent would be the force, and then they want us to identify two control variables. That would be the length of the wire, and obviously the current strength in the wire. Okay, then use the data provided in the table and the graph paper given below to draw a graph that shows the relationship between force and magnetic field strength. So there, I'm not going to use any graph paper. I'm just going to just try and draw this, right? So that's my y-axis and that's my x-axis. And so here I have obviously the B field measured in Teslas, and then here I have force measured in newtons. And then the relationship that I'm trying to look at here is force versus the magnetic field strength, right? Force versus magnetic field. Let me just write it in full. It looks weird if I just write B, right? So it's force versus magnetic field, right? Then I'm going to choose a scale here. Scale is straightforward. I'll just go up in twos. So that's 2, 4, 6, 8, 10. I'm trying to be accurate here. guys. So please bear with me. Then force is going up there in 50s. So that would be 50, 100, 150, 200, 250, 300. So I'm just going to go up in 50s there. Pretty straightforward. 150, 200, and then 250, then 300. So we see that when the magnetic field strength is 2, then the force on the wire is 50. When it is 4, the force on the wire is 100. When it is 6, the force on the wire is 150. And when it is 8, the force on the wire is 200. And when it is 10, the force on the wire is around 250. Right, guys? I tried to be accurate there. And then what I'm going to do is that I'm just going to throw a line starting from 0. Remember, my line should start from 0 because mathematically, if there is no magnetic field, unfortunately, the wire will not experience a force, because the force is experienced when the magnetic field around the wire interacts with the magnetic field of the permanent magnet. So if there's 0 magnetic field, then the wire would not experience a force. And pretty much my graph has to start from 0. It has to go beyond the last point as shown, right? It goes beyond the last point and the first point and starts at 0. And then obviously the next question then says we must calculate the gradient of the graph. And so the gradient is equal to change in force over change in the B field, which would then I can just choose any 2 points there. I could choose 250, right? I could choose 250 and well, 10 and 250. Let me just write those coordinates there. That's 10 and 250 and maybe 0 and 0, really, because 0 lies on the line. I've circled both the points I'm going to use. And so I'm just going to say 250 minus 0 over 10 minus 0. And so that should give me 25. All right, that is 25 as my gradient. Then the next question says we must use the force, or rather the formula F equals LBI sine theta and the gradient, all right, of the graph to calculate the current strength in the wire. Remember, we should know the length of the wire. And I'm not sure if that was given here, but the length of the wire is 2 meters. That's the controlled variable, right? Let me just add that there. I'm not sure how that was skipped in the question, right? The length of the wire is 2 meters. Yeah. So if that's the case, at least we have that other variable. Remember, the force is given by the equation LBI, all right, LBI, and we know that, again, the angle of the current and the B field here is also the control variable, and theta is definitely 90 degrees, right? It's 90 degrees for this experiment. So with that being said, we need to convert this equation into y equals mx, all right, plus c. Well, c is equal to 0 because the graph is cutting at the origin, all right? So if we convert that, we would get f is equal to, remember, our x values are represented by b, which means our gradient is represented by li. Okay, that's pretty much what our gradient is represented by. That is y. Y is the force, because y, the force represents all your y values. Then x is represented by the B field. So, and remember, you already have the value of the gradient. So if you equate your gradient, so your Li, and you equate that to your gradient, which is 25, remember, the gradient is represented by this part of the equation, okay? So if that's the case, then you could find the current by saying I is equal to 25 over L. And remember L, you were given L here as 2 meters, all right? So I'm just going to sub that in. That's 2, and so that should give you 12.5 amps. And that's a very, very large current. Okay, that's how you solve that. And the last question, which is 2.1, says the diagram below shows a simple motor. The direction of conventional current is shown as an arrow next to the cell. So that is shown here. Okay. And remember, guys, we're still dealing with motors. And so if we're dealing with motors, we are definitely going to be using Fleming's left-hand rule. Okay. 2.1.1 says we must provide labels for Y and Z. So Y represents a split ring commutator. Split ring commutator. And Z represents a rheostat. And remember, a rheostat alters the resistance of the circuit, which then alters the current. And current directly affects how that motor rotates. Okay. So 2.1.2 says we must determine the polarity of X, and because we are using conventional current, all right, so X should be negative. Then 2.1.3, is the motor above a DC or an AC motor? Well, it's definitely a DC motor because they have used split ring commutators. 2.1.4 says if the part labeled Y were to be moved, right, were to be removed, how will this affect the motor? Well, the motor will not rotate fully, basically. All right, it'll rotate, all right, up until a vertical point and then dangle in the middle. So split ring commutators ensure a full rotation of the motor. So this basically is looking for the function of the split ring. So you would say that number one, the motor will not rotate fully, which means complete, which means, all right, complete a full revolution, right? It will not do that. All right. So the motor will not rotate fully, which means complete a full rotation. Why? Because a split ring is not there, all right, to reverse. So the function of the split ring commutator reverses the current every half revolution to ensure a full rotation. So if that component of that motor is not there, unfortunately, the motor will not rotate fully. Then it says here, is side A to B moving into the page or out of the page? So if you look at side AB, and if you just follow the direction of current here, so current enters there, goes there, and then goes here. So current is going from B2 to A. So, right, that's the current. And then we have north. So, right, the direction of the magnetic field is moving from north to south. So it's moving in that way. Okay, so that's the B field and that's the current. And so if we use Fleming's left-hand rule, our thumb should be pointing into the page. Okay, so that's 2.1.5. That is into the page. 2.1.5. It is moving into the page. Okay. And then the resistance in Z is decreasing, which the current is obviously going to increase. The speed of rotation of the armature should also do what? It should increase. Okay. and then the poles of the permanent magnet are removed. However, current still flows into the armature. Okay, so now we just have an electromagnet. That's all we have. Draw the direction of the force on part AB, right, on the diagram. So here, what they want you to do, obviously, if you look at, if this is from, let's do it like this. So if we were looking at this circuit from here, okay, that means B, if you're looking at the circuit from there, current is going from B to A, right? So current will be going from B to A, and it will be moving away from your eyes. So it will be going into the page. So let me put an X there. So that's an X there, all right? There's an X there. And then on the other side, current will be coming out like that, okay? So if current is coming out of there, according to the right-hand grab rule, right, then on this side here, your field is going anti-clockwise, and your field there is going clockwise, right? So the field would look like that there. And we see that if there is a build-up of magnetic field here, because the field lines here are parallel, then that would push that side of the loop that way, and that side of the loop that way, right? That's pretty much what they're asking for there. Maybe it might not be asked clearly, but that's what they're looking for, because now it's an electromagnet. There is still a magnetic field in the armature, and that's pretty much what that's about. Then 2.1.8 says, apart from changing the resistance of part labeled Z, how else can you increase the strength of the magnetic field on the armature? So apart from, obviously, when you change the resistance, you change the current. You could also just increase the number of turns in the armature, right? So you could increase the number of turns in the armature, right? In the coil, basically, in the coil. All right, that was a long, long question, but I hope that helps. Cheers, thank you.